my name is Kevin Hartman, and this is my talk, starting from scratch, bootstrapping a compiler for fun and profit. Disclaimer, profit is not guaranteed, neither is fun. A background in compilers is neither assumed, implied, nor expected. Questions are welcome and will be answered, possibly correctly. So what's a compiler? It's a program that translates from one programming language to another programming language. To create a compiler, we need three things: a source language, translate from, target language to translate to, and some rules that say how to do the translation. So how do we make a really great compiler? There are two main ways to do this. A, write the perfect compiler on your very first try from scratch. Good luck with that. Or you can start out with a not so great compiler and use that to write a better one. And you repeat that until you succeed, or you're bored, or you go completely insane, or something like that. And all that's great, but what if you don't have the not so great compiler to start out with? What if you don't have a compiler at all? Modern answer is you just Google it. Someone will have written one for you by now. If they haven't, you start with an existing compiler for an existing source language, and you change the target language that it generates so that it just generates what you want. But if we were starting from scratch, like what we did back in the old days before we had the internet, we could just grab compilers from Google. What would we do if we didn't have a compiler to start from? Well, we'd make one. So there are many possible ways to go about doing this. Here's my approach. So what are we trying to do here? We want to write a program that can translate from the language we have to the language we want. But what language do we have? We don't really know yet, unless we know what system we're talking about. But we do know that almost, depending upon how you define the term, every computer has a built-in CPU chip that has a machine language hardwired into it. So all we have to do is use this machine language, understand that one language, and everything is all solved, right? Wrong. Because there's not just a machine language. Machine language is specific to a chip. So every CPU chip has its own version called its instruction set. Sometimes later chips are backward compatible with previous chips, like the 8086 series, ARM series, stuff like that, but sometimes they're not. And the instruction set that the CPU chip supports is part of the fundamental design of how that CPU is made. So the hardware features that the CPU implements are directly reflected by the CPU instruction set. So the odds that anyone is going to write a completely generic machine language that's going to work for all processors, probably never going to happen. Which means we can't just write a single universal machine language that will work for every CPU. So the best we can do is we'll try and find a generic approach, one that would work for a wide variety of processors and platforms. So here's our master plan. First, we will define a very simple bytecode language, one that's just barely powerful enough to write a compiler in. And then we'll design a generic compiler for our tiny little language with a set of requirements that hopefully we can implement on any machine that we like. And that way we'll be able to implement our small compiler using a small amount of machine language from our target machine. From there on in, we can use an existing compiler to write a better compiler to compile a nicer source language. And we repeat step 3 until we have the compiler we want, the language we want, or we give up in despair. So here is our very, very simple language. It has 4 instructions that are bytecodes. Bytecode 0 is exit with the program. Bytecode 1 is define byte n as having the following definition. And instruction 3 is quote. So bytecode 2 says just output the following byte. And lastly, any other byte that we have defined, we just output it. So based upon its definition, we just output it. And that's our language. That's enough to get started. Here's pseudocode for sort of a generic compiler that you could write that would implement that sort of language. So we're probably going to have some sort of program header, because we usually do. So we'll want to put out the bytes that compose that program header. And then we're going to have a loop where you're going to get a single byte in from wherever it is we're getting input from, because we are assuming that in order to have an input program that's translated to an output program, from somewhere we are getting input, and from somewhere we are getting output. Because otherwise, the whole point of a compiler just doesn't really work. So we are going to assume that somehow we can get a byte in, somehow we can get a byte out, and that's our function that gets a byte. And then we check, is it 0? Well, somehow we exit the program. If it's 1, we get a byte. In this implementation, we'll get a length, and then we'll set a bytecode table with that length and that data. So, and then when we get a quote, well, we get another byte and we put it straight back out. Otherwise, we look up the byte that we were given in our bytecode table and we write that out and we run it. And here's how you'd write the same sort of thing, except written more in an assembly language sort of style. We'd have a loop, and then if we basically do a bunch of tests. If code's non-zero, we jump to the next. If code's not 1, we jump to the next. If code's not 2, we go to write out the value. That sort of thing. So what do we need in order to actually make this? Well, we need to know what the header is if we're going to write out a header. We need to have some way of getting a byte from our input. We need a way to send a byte to our output. We need to be able to compare a byte to a constant and branch if they're not the same. We need to be able to go to a fixed address. We want to be able to exit our program. Technically, that's a nice to have, but it's a very nice to have, so I'm including it. We want to be able to add or increment an address. Just about every machine language will have that. Get the address of an area of memory that we've already allocated somehow. Set a byte at a given address that we specify. Get a byte from an address we specify. Allocate or reserve a certain amount of memory, whether it's fixed or dynamically. And with our put bytes function or get bytes, well, that's the same thing as getting and putting a bunch of bytes in a loop. Everything that we have there, we can accomplish that. Other things we need to know based upon our hardware and our operating system. First of all, how do we write a valid program in the CPU instruction set? What are the rules? Does my program have to start at a specific memory address? For example, does it have to be at a memory address that's divisible by 4, like on some machines for alignment issues? You must or may not execute certain CPU instructions in certain modes. ARM, for example, can be set into thumb mode where it understands 2-bit instructions, or ARM mode where it understands, or sorry, not 2-bit, 2-byte. 2-bit's a little small. Yeah, or 4-byte instructions. So things like that we want to know about. Rings for assembly language permissions, whatever sort of restrictions our CPU has about how it runs, we need to know a little about that. We also know how to load and run a program on our system. For example, if we're going to be running under Linux, well, we usually have a shell
and then we can run a file with a specific header and permissions written in something like format like something called ELF. Under Mac, Mach-O is their executable file format. .com was MS-DOS. There's Windows P formats. So whatever the executable file format, whatever the permissions are, we need to be able to match that so we can make our program actually run. On the other hand, we might not even have an operating system. So maybe what we need is a specific bootloader or block address, like uboot has a specific address. When you want to write things for ARM, you just put it at a specific address on your SD card and it will boot from there, for example. Grub is a bootloader that looks at a specific spot on a hard drive. Or you might actually be just uploading your program with a specific voltage on a specific set of pins over a serial device. PIC-10 chips work like that, for example. So no matter what it is, we need to have a way to do it. And lastly, like I said before, we need some way to get data in and out from our program, or our program really can't be a compiler. So how can we do that? Well, if we have an operating system calls, one way. Do we maybe have to call a device driver to get the data from the device we want? Is the data we want memory mapped into a certain hardware address? We just have to access that memory and then come back and maybe set another instruction and check again. There's systems that work like that. Do we have to use some specific hardware instruction? Or are there other special memory addresses that are defined by the operating system or by the hardware itself that we need to use in order to get data in and out from the device that we want to provide our program with and the one that we want to send it out. So somehow we've got to figure out those things. They're all important. They're all things that are going to be assumed we've solved at this point. So here's the example of that compiler for an ARM 7 thumb instruction set for an Android cell phone. And if you're really, really interested, I've got an appendix at the end of these slides where people can go and check out how the assembly language gets written for that. But since not everyone necessarily is interested in ARM assembly language, this gives you an idea of how small our program can be. The stuff in blue is the header. So our actual program starts with write header in red. And the stuff in green is the loop. Exit is a handful of instructions. Defining things is a bit of work. Writing out a string and getting a byte. And all in all, that's something that you could pretty much type in if you had to by hand, and it would execute. So you don't have to assume a compiler necessarily has to be huge as long as it doesn't do a lot. So what now? We have a minimal compiler for a tiny language, and right now we'll even pretend it works. So what's the next step? We'll invent a better language using our existing compiler to implement it. So how do we do that? Well, we have a define statement that lets us define bytecodes. So what if we make a language that's made out of individual bytes as symbols that are meaningful to the language? That way we don't have to do a lot of work parsing or interpreting anything, and we can still get something that's a little nicer to work with than pure machine language. So, and with that, we'll have something that's friendlier to write a compiler for our new language, and we'll be able to write a compiler for our symbolic language in our symbolic language, and then we'll be able to compile that, and then we'll be on our way to actually writing something that we want to keep.
So outline for our new compiler with our minimal little language. For each symbol in our language, we are going to define using bytecode 1, which is Control A, by the way, which is why that's on the screen there, as the symbol that are machine language instructions that we're going to run for that symbol. And then for the rest of our program, whenever we write a symbol, our program is going to be smart enough to know, hey, that's what I output for this. So we are 90% of the way to writing our bytecode compiler right now, because once I say define symbol open squiggle as start a loop, everywhere I write start a loop, it will put down the code that starts a loop. Wherever I put down, code for end a loop, we'll have end a loop. We basically got a very handy macro processor. And that is pretty much enough to get started writing things. So if we want to output a specific byte as an argument to a machine code, we can use our quote to quote the byte, so we can output a specific byte if we want to set something to a specific value, and then have that byte be an argument that comes into our symbol. We arrange the order in which the symbol is written so that it matches where it needs to be in bytecodes. And of course, at the end, we'll need to end our program with our exit symbol. And that's sort of the sketch of our new compiler. So what's our new language going to be like? We'll go crazy. We'll give it 3 variables, A, B, and C. And what do we want? Everything before was pure machine language. So let's try and get at least less control codes and more printable ASCII characters that we can read. We'll try and allow comments, nested loops, conditionals. Let us add and modify symbol definitions. So here's a new language. Semicolon is a comment to the end of the line. Hex is an optional thing, which we will implement in a more complicated version of this. Quote outputs an individual byte unchanged. For our looping and calling, we have a similar, sort of symbol. We are going to push where we are on the stack, start a loop, and we are going to return back from where we are when we end a loop. You can break from a loop just by popping something off the stack. So when we say to go back to that, we go back to the previous place. If we want to skip ahead as a go-to, we can skip 10 bytes. If we want to go back to somewhere we were, well, we store where we were on the stack and pop our way back to it. When we want to quit, we'll exit. Our conditionals that turn out to be useful for this compiler. Check to see if something's false. We'll skip ahead in bytes in our machine code. And do a less than equal comparison and do the same thing. And we can compare 2 values. First, comparing a constant. This is an example of where we might want to quote something. And then we can see whether they're equal, whether they're the same. We can check to see whether our constant C is null. A handy feature is just going to be to write up the header. So that we define the definition of our header, then put in H, and immediately our program will write out our header. We'll get a byte, we'll put a byte, string will write out a string with A and C in it, although it doesn't actually say that on the screen. Something that will be useful for defining tables is specify this spot here in the code offset by this bit. And then we can inline data that we want to be able to read. Specifically, we can inline definitions for when we want to be able to compare something existing to something that we run into in the future. So we are going to be able to store the address of this spot plus an offset to somewhere else. Most languages will let you do this somehow. You might have to push a value onto the stack and then manipulate it, but usually you can grab that somehow and modify it. So, and on some architectures, they have things like a Harvard architecture where it's difficult to reference code versus data, but there's usually a way around that. So that's usually implementable one way or another. That's perhaps the most difficult one, depending on the feature set you have. You can check to see if there's a value at a given address and what that, set C to that value. So get a byte. You can move, advance our pointer by 1 byte, and we can set C to it. We can decrement B, which is going to be a counter. We can copy a value. We can multiply. We can add. Times in this case is just a constant multiply times 16. And plus is just adding our two variables together. So here's our new compiler in 4 slides. I think it's 4 slides. So we print our header. We start our loop. We skip over here plus 2 statements. Oh, we set A to be here plus 2 statements, which is the start of our table. Then we skip over whatever length our table is. And here's our table where we define the symbols that we will use for a compiler. So H, the lengths. The definition is purposely left in yellow just as the name because it's going to vary depending upon the implementation. I did come up with, again, an implementation for ARM thumb, and again, I am not going to bore everyone with it unless they actually want to go and take the time to look at it. So, the next step, we read in our byte. We check to see if it's, in this case, character 4, which is following a Unix convention for end of data. So if it's Control D, we want to exit. If we were following some other convention like MS-DOS, I use Control Z, so we look for a Control Z character, and if so, we'd exit. Otherwise, we skip. If we don't exit, we skip on to check. Okay, is it quote? And originally, I had hexadecimal, processing in here, and then I realized I didn't have it right, which is what happens when you try to be too complicated. No, I did have it. I did have it right. It was just I had to add 2 byte units. That was it. Anyway, so if it is a quote, we read in a value and write it back out. So B becomes a value read in, and then we write B back out, and that's our quoted thing. Then we go back to our main loop and pop our value back off. Yes, we do have a hexadecimal command. So if it's X, we skip the length of X in whatever number of assembly language instructions this is. This is not the most convenient yet, because whenever you jump over something, you have to know how many instructions you used and how big they are in order to say how far to jump. But that is something we can live with until we write something more convenient. We already are seeing a compiler that can do it. And so we read something in, we check to see if it's quoted, the character 0, 0, and we subtract that. And we are assuming here that no one is ever going to do something horrible like try and get the hexadecimal value of something that isn't a proper hexadecimal character. We are absolutely perfect with our inputs and never make any mistakes. Yes, that's it. Actually, we can be more lax with our compiler if we're the only ones using it, because we only have to get each compiler right to the extent that we can actually write something more powerful and go back and fix what we've done. So we can add checks at the point where we get to, a language where we're happy enough to start adding them in. And that will probably be with this language or the next one that you would write, I would imagine, because while you've still got the ability to build them into the assembly language level is a really good place to put them. So yeah, we check to see if it's less than 9, and if so, oh great, that's its value. Otherwise, as it happens based upon the ASCII character chart, it's 7 higher, so we'll subtract 7, and that'll give us the right value. And then we will do our multiplication, which in this case is always by 16, which just happens to be the amount that we need to shift over to get our next digit. Wonder why I invented that back code. And then we copy over the value of that byte into C, which is where we're going to keep this. And then we are going to read it a byte into B and do the same thing. And then we're going to add the two, and we're going to write it back out. And here's our comment handling. We check to see if it's a comment. If not, we skip over it. A loop. We will read in a byte, and then we will see, is this character 0A, which is new line for Unix people. And if, we can use DOS conventions here if we want DOS, and check for character return new line or whatever other sort of end of line or end of file handling you want here, but whatever. So if it is that, then we pop the loop that we just put on off of the stack and do an end loop, which will return us right back to our main loop. Otherwise, we'll just end this loop and keep looping around and get another character. And lastly, we have our table lookup, which is in a loop. We get the byte that's at the start of the table, check to see if it's the end of the table, and if it is, we go back to the main loop. So if there's, someone put in something we don't recognize, like say a space, which I deliberately didn't define, then our code does nothing, so we can indent freely however we want, put in comments. Life is already getting good. We can then check to see whether or not, okay, is the character that we have there equal to the character that we got. If it is, then we write out the definition for it, which is we get the length, and then we write out the definition. So, and then we go back. Otherwise, we get the length of it and skip ahead to the next entry in the table, which happens to be that address plus that length. So we do that, and we have already got a compiler that we can use to write some basic programs, including itself. And from here, what next? Well, whatever we want. We can define new codes in terms of machine code. So we can add new definitions to our table. We can change existing code definitions. We can always build something else if we don't like the way our current code is being compiled or generated. So where do we go from here?
We can add mathematical features. Memory access is probably going to be one of the next ones, like, say, the equivalent of a malloc or something like that, which is really easy on, say, ARM assembly or Unix, where it's just add a system call. Our read and write a byte or just system calls, so we already presumably know how to do that on a lot of architectures. String handling is mostly just loops, and reading and writing bytes. I/O could be system calls, could be whatever, but we figured out how to do at least a byte of it. We want to write somewhere else or different file systems other than a default or something like that. And start exploring how to do that. You might even want to start adding, other annotations like types. We already have comments in whitespace just in our language there, but we're free to start building up to something more like, a C compiler or whatever we want. The most obvious thing that you would probably want to do next is, instead of having a single code, bytecode, implement strings, and then you look to see whether this string keyword matches what you're looking for. So you don't have to restrict yourself to single byte symbols. But all of that's easier to do now that you've got a language that you can actually write comments and spaces and all of those nice sort of things. So that's where we'll go next. And that's my overview on how to get started bootstrapping on Python. And if anyone is interested, I do have my appendix on my ARM code example. I have a disclaimer. I've only written it, but I haven't actually tried running it. So it may not actually work. But I have hand-assembled ARM thumb code before for a similar learning project that was an interpreter rather than a compiler, and that did run. Of course, the machine it ran on doesn't run anymore, but, it ran. And I had a very small hello world. So if people are interested in the details, they can stay. If you're bored at this point, you can feel free to leave. It's going to get technical from this point in. So a real world example, my cell phone runs Android, which is a version of Linux. Linux runs machine language stored with a valid elf header. There's where you can find it when you look up in the slides if you like. There's the instruction set for the CPU, which we need. The Linux system call manual pages specifies how to do system calls. Specifically, you use the software interrupt instruction with the system call number in register 7, and the result ends up in register 0. And there's a system call table that defines system calls exit, read, and write, which are ones that we will need. And as an example of the sort of thing that you're looking at, this is what the instruction set summary for an ARM 7 compatible CPU looks like. And those are the actual bit patterns that you can use and plug into a program with the right header, and it will run. So, for example, if you look at line number 3, it starts 001 op, and if that op is 0 for move, for example, and RD stands for the destination register. So we can also make that register 0, in which case we would have a hexadecimal value of 2, 0. So 2, 0. And the offset is the immediate value, as in the byte you want to put in. So 2, 0 and the byte loads register 0, that byte, which is one of the things we might want to add is our symbol, set register or variable b to a constant, or something like that. And depending upon the byte order,
We basically use the byte order of our byte code to match the byte order of our language. And then we just say, okay, literal byte of, say, 3, 20 is going to set our byte to 20. Don't have to remember that it's 20 ever after again once we defined it. And we can move on. And in general, you can go through and you can work out what all these things are by hand if you have to. There are assemblers and other programs that exist now that do this sort of thing much easier. But this talk is about starting from scratch, so this is how you actually start from scratch. Let's do our checklist to make sure we've got everything we need for our very starting compiler. Well, we need to know our header and our length, which the alpha header specification will tell us. We need a way of getting a byte in. Well, sure, system call read, single byte. System call write to put a byte. Do comparison. Yeah, well, we've got to compare against a constant instruction, and we've got a conditional branch. And go to loop gives us an unconditional branch. And we want to exit our program. My system call to exit. Add and subtract. Got all these instructions. And for our bytecode table, there's a rule in our elf header. If you bother to, read through all the gory details, it says you can allocate space to your memory image. So we're just going to say, yeah, we are going to make our memory 64K bigger than it has to be, and we're going to make it writable. So we just do that, and we make sure that we don't write over our code, making everything writable, read-writable, and executable, which is generally not a good thing to do unless you are starting out, trying to write something that you can actually write something sane with. So here's our example, finished example, and here's where it actually comes from. So there's an elf file header that defines the versions and how much, there's some unused padding in it. There's a section header, there's an offset to a program header. There's the number of section headers, all of which are 0 because we don't have any. We don't actually need them if we're putting everything in one section. And again, the goal here is to make everything as simple as possible so that as few things as possible can break until we have something that we trust a little more, and then we work from there. So we have to write an elf program header. Program types load. If I did the count, and the offset is actually 52 bytes, and when counted in hexadecimal. So the starting address in memory is going to be 08052. Everything's in reverse byte order because we said byte order with little endian, which is a convention, at least on the ARM chip, that I was working on when I first came up with this idea of working on this stuff. So that's what I've stuck with. But it's actually a lot easier to read, normally when it's big endian, but since I'm presenting it from the point of view of each individual byte rather than the words, I'm writing them. I just remember to write them in the order that they need to be for everything to work, and work from there. So that's the elf program header. Okay, here's the actual code. So to write our header, we need to set ourselves up for a system call. So we say, system call that we are going to want to do, you said had to be in register 7, so we're going to put number 4 into register 7. That's the 0427. And I'm going to set register 0 to be standard output because the arguments go from register 0 on to register 6, whatever system call you want. And then we are going to be tricky, and we say register 1 is going to be the value of register 15, which is our current position. in the program plus 4 bytes. That's how, that's basically how they handle branching. They have a specific register. It's the instruction pointer, and you can read and write to it on ARM. So I'm reading from it. I'm subtracting 4 from it to get the length of our header. And then, I'm subtracting our header length from it to get the start of our header. And I'm adding 4 because it's because we're subtracting away the extra 4 that it's added. So we're backing up by just the right amount to get to the header we want to write. And then we say how long that is, which is 54 bytes. And then we say 00df, which is system call. Then we set R5 to be at our current address plus 255, which is basically way off into the 64K of memory that we wanted. So that's going to be our bytecode table. It's our starting load address plus 255. And as long as our program size is less than 255 bytes, we're golden. And as it turns out. So from there on, we have our loop, which really is just a destination to branch to. So here I'm setting up, there's a convention on ARM, R14. R14 is where you are going to return to, and R15 is where you're actually going. So, and since it always adds 4, it gives you just enough space to say, store this current address where I'm going to be coming back to, and do the branch. So that's why it adds 4. That way you can always say, yeah, you're gonna return to here plus 4, which means you're doing a function call and coming back. And so that's what that does. We branch to the spot where we define a byte. We do our comparison to see if it's 0, system call. We do a comparison against the constant to see if it's a quote. Branch to our byte instruction. We subtract 2 from our bytecode number when we store it internally, just to save space, of course. It's, 64K, that's extravagant. And we are shifting everything by 8 bytes to get our address, because we are saying each bytecode can be 256 bytes long. You notice that's what we're taking in as our parameter for read is at most 1 byte. So since our length is 1 byte, everything's going to fit to a table that's 255 and 255. So it will fit within 64K. Everything will be happy. And we can read in our byte definition. First we read in the length, and then we set the length that we want to read based upon the length that we read in, and we do another read. And then we enter define, so we branch back to our coding is basically the same sort of thing, only uglier. Instead of doing greater than, less than, for read in, read out, we set up the call, read in, read out, C, and I want to branch back to loop, but I have address XX in there because I couldn't figure out how far back to branch at the time when I wrote that and finished the clock. So that, for example, will not execute. And write is basically setting up a write system call. Same sort of way, we're going to shift by 8 to find, our fixed offset in the table. And that will give us where we need to be for our address. We get the length, we write it out. Get a byte is really short. And yeah, that's it.